We're now going to take up a particular problem that has a very non-trivial solution. We assume the stream elements are bits, zeros or 1, and we want to know how many bits in the last n are 1. If we can store the most recent n bits, we could use a solution like the one discussed for averages. In fact, the algorithm would be even simpler. However, we're going to address the situation where n bits don't fit in main memory. Perhaps n is a trillion, or n is a reasonable number, but there are so many streams that we can't store complete windows for all. If we want exact answers, then we can show that it is impossible to do anything better than to store the entire window. However, what is interesting is that we can store on the order of the square of log n bits, where n is the window size, and still answer queries about the count of ones with answers that are off by at most a small factor, as small as we like if we do enough work. The problem we're going to discuss is this. We're given a stream of zeros and ones. At any time, we have to be prepared to answer a query of the form, how many of the last k bits were 1? Here k can be any integer from 1 up to some large upper limit n. We can surely do this if we use a window of size n and store the last n bits. When a new bit arrives, we throw away the oldest bit in the window since it can never again be useful to answer one of these queries. But one disadvantage of this approach is that answering one query requires that we examine k bits. Since k can be quite large and both inputs and queries may be arriving very rapidly, that may be time we cannot afford. Another potential problem is that we may not be able to afford the space. As we just mentioned, we could be trying to handle a large number of streams, or n could be so large that even one window does not fit in main memory. Both these concerns suggest that we should consider a method that uses less than n space, and that also allows us to answer queries about the last k bits much faster than on the order of k. It turns out that we can't get an exact answer to queries without using n bits in the window, but we can get close using much less space than O of n and also much less time than O of k. We're going to introduce the right algorithm with a discussion of something that seems like it should work but doesn't quite. Our goal is to be off by no more than a factor of 2 in estimating the number of ones in the last k bits. So we will summarize blocks of the stream. Those blocks will have exponentially increasing lengths, that is 1, 2, 4, 8, 16, so on. And the summary of a block will be simply the count of the number of ones in that block. When we want to know the count of ones for the last k bits, we can find some blocks that lie wholly within the last k bits, and we add up their counts. It is only the last block, the one furthest back in time, that gives us pause. We don't know how many of its ones are within the last k bits, so we have to guess. But if we created these exponentially growing blocks for all time units, then there would be as many blocks of length 1 as there are bits in the window, as well as blocks of size 2, 4, 8, and so on. So that saves us nothing. Instead, we have to drop blocks if their left end, that is, the end that is earliest in time, coincides with the left end of a larger block. And we also drop a small block if there's a larger block completely to their right, that is, later in the stream. As a result, you never have more than 2 blocks of any one size. So here is an example of the blocks we might retain at some time. The 5 rows of blocks are of lengths 1, 2, 4, 8, and 16. Okay. There are 2 blocks of length 1. The more recent has a count of 0 because it consists of a single 0. That's this. While the other has a count of 1 because it consists of a single 1. Okay. Here's a block of length 2. Okay. It has a count of 1 because it represents 0, 1. That is, these 2 bits. Notice that we've previously deleted the block of length 1 that would go here because it begins at the same point as the block of length 2 above it. Also, all other blocks of length 1 are deleted because they have a block of length 2 completely to their right. We also show a second block of length 2. Its count is 2 because it represents this 1, 1. There are two blocks of length 4, and they have counts of 2 and 3. They represent, well, this guy represents this sequence 0, 0, 1, 1, so it has 2 1s. This represents 1, 0, 1, 1, and therefore gets a count of 3. Okay. We see one block of length 8. Its count is 4. Well, let's see. Because it represents these 8 bits. And notice that the count for a second block of length 8 is not needed because we can figure out it has 6 1s, since that 6 is the difference between the number of 1s in this block of length 16 and that block of length 8, that is 10 minus 4 equals 6. So if this block existed, it would have surely have 6 1s. Okay, now suppose we get a query for how many 1s there are in the most recent 28 bits. We can add up the counts of certain blocks, some little blocks at the right end and some bigger blocks going to the left. We want to pick blocks so that each of the most recent 28 bits is covered by exactly one of the blocks we choose. So we pick this block of length 1, okay, this block of length 2, this of length 4. We don't want this block of length 8 because we have this block of length 16, and that's still all within the last 28. Okay. So far, we have covered 23 bits. And we know that among them, the number of 1s is 0 plus 1 plus 2 plus 10, which is 13. Okay, but what do we do about the oldest 5 bits? That is, they're these bits. Now, if we could see the bits, we would know that they're 0, 0, 1, 0, 1, and therefore they have 2 1s. But we don't see them. All we see is that they are part of this block of 16, and we know that block has a count of 6, okay, but we can't tell how many of those 6 are in the most recent 5 positions. Again, we don't ever get to see this anymore. Now, if we could see them, of course, we would know there were 2 and that the right answer is 15. But we need to estimate, without seeing, how many 1s there are in this region. Okay, if we guess that half the count of the block, that is 3, or 6 divided by 2 in this case, is in the region we don't see, then we would guess 16, and that's only off by 7%, so that's not even bad. We could even try a proportional guess. That is, say we know that there are 6, in 6 divided by 16, well, 6 divided by 16 is the probability that any given bit is 1 in the range represented by this block of 16, and we know that we have to count 5 of them, so that's 30 divided by 16, which is roughly 2. And so if we guess 2 and added that, we'd get 15, and that happens to be right on the mark, even though we didn't get to see the 5 bits that we wanted to count those. The strategy has a lot to recommend it. Okay. First, it stores only the square of log n bits. I might comment that we use this expression, log super 2n, to mean the square of log n. Okay, this is a common expression. You don't want to write it as log n squared because that's really 2 log n, which is not what we mean. So I should, if you've never seen this notation before, again, putting the square above the log means that you're actually squaring the whole thing, squaring log n. Okay, now, as I said, storing square of log n bits is not that bad. Okay, it's much less than n for large n. So if n is 1 billion, then log squared n is about 900. Now, why do we need only on the order of log squared n bits? Well, first of all, if the window size is n bits, we never need any blocks of length greater than n. And a count up to n can be stored in log base 2 of n bits. Now, how many counts do we need? Well, there are only log base 2n block sizes from 1, 2, 4, 8, 16, and so on, up to the largest power of 2 that is no larger than n. So we never store more than 2 blocks of any size. And as a result, we need to store at most 2 log n counts of at most log n bits each, and that's 2 log squared n. Another good thing is that after each bit, we do a limited amount of work. We have to create a new block of length 1. For each of the lengths 1, 2, 4, 8, and so on, we may have to drop a block of that length, or we may have to combine 2 blocks of one length into 2 blocks of the next larger length. But that means at most order log n work total, since there are log n sizes. And the error is frequently small. It can't be bigger than the count of the biggest block, the one that is only partially in the region we're counting. There's a problem with the scheme, however. When the ones are distributed evenly among all the regions of the stream, the number of ones in the ambiguous region can't be more than half the total number of ones in the region we want to count. So our error is limited to 50%. But look what happens if all the ones in the region we want to count are at the left end, and in particular are counted only by a block that is partially within the desired region. Then the true count could be anything from 0 up to the full count of that block. Anything we guess could be wildly wrong, and we'll never know. We're therefore going to discuss a similar algorithm that preserves the good and avoids the problem with uneven distribution of ones. We'll still divide the window into blocks, but instead of letting each block cover a fixed segment of the stream, we'll let each block cover a fixed number of ones. The sizes of the blocks will still be limited to the powers of 2, that is 1, 2, 4, 8, and so on. But the notion of the size of a block changes. Now the size of a block will be the number of ones. So we'll have blocks of size 1 to represent segments in the stream that have a single 1. Blocks of twice that size will represent 2 ones and any number of zeros. And then there will be blocks representing 4 ones and any number of zeros, and so on. The advantage of this scheme is that if there are a few ones in the recent stream, the block sizes covering that region will stay small. They will cover large parts of the stream, while their size, or number of ones, remains limited. I decided to call the algorithm I'm going to describe the DGIM algorithm. The initials refer to the 4 guys who invented this algorithm, Mayur Datur, Aris Yonas, Pyotr Indyk, and Rajiv Motwani. And in fact, this is a good time to stop and remember Rajiv Motwani, who died shortly after this algorithm was published. He, along with Yonas and Indyk, is also responsible for locality-sensitive hashing, which forms a major part of this course. Like our earlier attempt at an algorithm, DGIM stores on the order of log squared n bits to represent one n-bit window. There's an absolute guarantee of no more than 50% error in the answer to any query. And if 50% is too much, you can reduce the error to anything greater than 0. The algorithm becomes more complicated and the number of bits you need to store grows, although the number of bits remains proportional to log squared n. It's just the constant factor that grows in inverse proportion to the desired error bound. Okay, to begin the story, we need to introduce the idea of a timestamp. Every bit that arrives in the stream gets a timestamp. You might think that we need an arbitrary number of bits to represent the timestamp, since there's no limit on how long the stream can be. But it's really only necessary to represent timestamps modulo n, the window size. That is, we can divide the timestamp by n and take the remainder. The net effect is that timestamps start out at 0, 1, and so on, up to n minus 1, and then go to 0 again, 1, 2, and so on. Regardless of where the window is in the stream, its n bits will all have different timestamps. We're going to partition the window of length n into buckets. Each bucket is represented by a record, and records can be stored in on the order of log n bits. As we shall see, we only need on the order of log n buckets to represent the window, so on the order of log squared n bits suffices. The record contents are the following. The timestamp of its end, the most recently arrived bit. As we mentioned, we'll record timestamps modulo n, so we need log n bits to represent the timestamp. The number of ones between the beginning and end of the segment. We call this count of ones the size of the bucket. However, the number of ones in the segment represented by a bucket must be a power of 2. That explains why we only need log n bits to represent the count of ones. We can store the logarithm of the count instead of the count itself, since we know that log base 2 of the count must be an integer. The count itself can't be higher than n, so its logarithm can't be higher than log base 2 of n. Since the logarithm is an integer I, and we only need log I bits to represent I in binary, log n bits suffices. It really doesn't matter much, since we still need order log n bits in the record for a bucket just to store the timestamp of its end. The partition into buckets must obey the following rules. There must be 1 or 2 buckets of each allowed size up to the maximum size we need. Remember that allowed sizes are the powers of 2. No bit of the window is part of 2 buckets. Some zeros in the stream may not belong to any bucket. It doesn't matter. But buckets can only increase in size as we go back in time. The most recent part of the window is represented by the smallest buckets. When the n timestamp of a bucket is more than n time units in the past, it no longer represents part of the window, so we delete it from the set of buckets whose records are stored. Here's a picture of what the partition of a stream into buckets might look like at some point. The most recent 2 ones are in buckets of size 1 by themselves. It's here. Further back, the previous 2 ones are grouped into a bucket of size 2. That's that. There might be 2 buckets of size 2, but there could also only be 1, as in this case. Then going further back in time, we see the previous 4 ones in a bucket of size 4. And the 4 ones before that are also in a bucket of size 4. Then we see 2 buckets of size 8, and finally a bucket of size 16. The n timestamp of this bucket is still within the window of length n. That's this. Although its beginning is outside the window. We still need this bucket, but any previous buckets have a timestamp that is prior to the beginning of the current window, so we have deleted their records. So let's see how we manage the buckets as bits arrive on the stream. The first thing we're going to do is worry about whether we need to drop the oldest bucket. We need to keep outside the bucket representation a count of the number of bits that have ever arrived in the stream. However, we only need this count modulo n, so an extra log n bits is all we need. When a new bit comes in, increment that count. Of course, if the count reaches n, then we set it back to 0. That's how modular arithmetic works. Now, look at the end time of the oldest bucket. If its timestamp agrees with the current time, then that timestamp is really the current time minus n, since we're computing all timestamps modulo n. The entire oldest bucket is therefore out of the window and we delete its record. But if the timestamp is anything else, then the oldest bucket still has its end within the window, so it remains. What we do next depends on whether the bit that just entered is 0 or 1. If it's 0, then we make no further changes to the set of buckets. That was easy. If the current input is 1, we have some work to do, but the work is at most logarithmic in the window size n. First, we create a new bucket for the new bit. The size of the bucket is 1, and its ending timestamp is the current time. There might have been 1 or 2 buckets of size 1 previously. If there's only 1, now there are 2, and that's fine. We're allowed to have 1 or 2 of any size. But if there were previously 2, now there are 3. We can't have 3 buckets of size 1, so we combine the oldest 2 into 1 bucket of size 2. Combining consecutive buckets of the same size is easy. We add 1 to the logarithm of the size, and we take the end timestamp to be the end timestamp of the more recent of the 2. So, for example, here are 2 buckets, could be of consecutive buckets of any size, say 2 to the x. We combine them into 1 bucket of size 2 to the x plus 1 by simply this bucket gets this ending time, let's just copy it from here, and we add 1 to the size, which essentially says therefore the size is doubled, and then we just make that go away. But our work might not be over. If we had to create a bucket of size 2, we might now have 3 of that size, so we combine the earliest 2 into 1 bucket of size 4. And the problem could ripple through the sizes. If we just created a 3rd bucket of size 4, then we could have 3 buckets of size 4. We need to combine the earliest 2 into a bucket of size 8, and so on. But because we're doubling the bucket size each time we pass the problem to the next level, after log n fix-ups, we have reached a bucket size as large as the entire window, and there's never a need for a larger bucket. Okay. The rippling effect therefore stops after at most log n rounds, and each round takes a constant amount of work. So O of log n is a guaranteed upper bound on the total time needed to process an incoming 1. Usually the time required is much less, and on the average it is constant. On this slide, we'll see the changes that occur as bits enter the system. So here's the initial state of the window. A 1 enters. We create a bucket of size 1 for it. This. But now we have 3 buckets of size 1, so we're going to have to combine the 2 earliest ones, this one and that one. Okay, so here we've done the combination. What has happened in terms of the records is that the record for this bucket is deleted. The size for this record has changed from 1 to 2, and its timestamp has not changed. It has therefore actually become this record. And notice that that 1 is really inside the record. The slide is not shown perfectly there. Now, I'm showing what happens after another 101 arrives. Okay. The first of these ones created this bucket, and then the 0 came in, represented nothing changed, and then this next one arrives. And now we get a third bucket of size 1. Okay. So that causes these two buckets to get combined into this guy. And now we have 3 buckets of size 2. So we have to combine these two, and whether that 1 really belongs in the middle bucket of size 2. So we combine these two into a bucket of size 4, and that made 3 buckets of size 4. So these guys got combined into that bucket of size 8, but that was a third bucket of size 8. So these buckets of size 8 got combined into that bucket of size 16. Now there can't be more buckets of size 16. There's this one, but that extends beyond the end of the window. So we're done rippling changes to larger and larger buckets. Now I want to explain how to query the system. So suppose we want to know how many ones there are in the last k bits, where k is any integer less than or equal to n, the window size. The first thing we want to do is to ignore all buckets whose ending timestamp is earlier than k bits prior to the current time. Those buckets are all outside the range we want to count, so they make no contribution. Start by summing the sizes of all the buckets except the oldest bucket that is still in the range we're interested in. Then add half the size of that bucket. Okay. The reason we only add half the oldest bucket size is that we really don't know how many ones from that bucket are still within the range of interest. By guessing half, we minimize the maximum error, as we'll discuss on the next slide. So here's why the estimate can't be off by a factor of more than 50% from the true answer. First, suppose that the oldest bucket in the range we're interested in has size 2 to the I. We assumed half, or 2 to the I minus 1 of its ones, are among the most recent k bits to arrive. The true number could be anything between 1 and 2 to the I, so our error is upper bounded by 2 to the I minus 1. Now, what's the smallest the true answer could be? There's at least one bucket of each of the sizes less than 2 to the I that lies completely within the last k bits. These account for at least 1 plus 2 plus 4 plus so on up to 2 to the I minus 1, and that's 2 to that sum is 2 to the I minus 1. Now we add 1 for the one that is at the end of the oldest bucket. That bucket has an ending timestamp that's within range, and buckets always end in a 1, so there are at least 2 to the I ones within the range. Okay. Since our error is no more than 2 to the I minus 1, that error is at most 50%. Now, we're not going to discuss the extensions here, but it is possible to modify the algorithm described to limit the error to any fraction we like greater than 0, while still using only on the order of log squared n bits to represent all the buckets we need to represent. The textbook describes how to do this.